Okay, so let's get started. Before that, let's go through a quick review or recap of what we did in the last class, right? So essentially, we started looking at what is called the inner product, right? So how do you generalize the notion of similarity or the dot product of two vectors, right? And we listed out all the properties of a simple dot product, and then we generalize that to any function, right? It takes two vectors and maps to a number. So what are the properties that this particular function should satisfy so that it can mimic inner product? Then it turned out to be, it should be bilinear. That's one property. If you take inner product with itself, it should be non-negative, and it should be symmetric, right? So these are the properties. Of course, if you are working with complex numbers, then it's not symmetric that way. It's Hermitian symmetric, or U Hermitian V is same as V Hermitian U. So it's not. So it's not like V transpose U is same as U transpose V, but V Hermitian U is not same as U Hermitian V, right? So there is a conjugation difference. So you have to take care of that. Okay, so then we looked at what is called the induced norm, right? For example, if you look at A transpose A, that gives me the Euclidean length squared, right? So similarly, if you take any inner product of a vector with itself and take the square root, that should induce what is called a norm, right? So this is the norm induced by the inner product. So that's what we looked at. And then we also saw that this norm, or the notion of length, satisfies certain properties, right? First of all, it's non-negative because it's length. The second thing is, if you look at the length of the scaled vector, it should be the length of the vector scaled by that much, right? It's a modulus of alpha times the vector, and the triangular inequality. And this length notion will induce distance, the distance based on length. Similarly, if there is a norm induced by an inner product, then the distance can be written as norm of U minus V, right? This is the distance. This is a distance notion induced by this norm. So when you look at a space, a vector space with an inner product and an induced norm, that space is called what is known as an inner product space. Okay, for example, Rn is an inner product space, and there are so many others. We will look at few more today. Okay, so now then we also saw an example of how to, for example, if you have not so intuitive space, and we have to measure similarity, how do you do that? Well, towards that, we saw that, we looked at this example. You look at all functions which are continuous and square integrable. I can define my own inner product here, and that inner product will induce a norm, and therefore it becomes an inner product space. And I can also define the distance, and naturally I can define what is known as similarity of two functions. All that I have to do is I have to take F4 norm of F, G over norm of G, and take the inner product, right? So that gives me this notion. So this also leads to, if you do the same thing for random variables, it leads to correlation coefficient, right? That's what we did in the last class. And then we also looked at a very important inequality called what? Cauchy-Schwarz inequality, right? So essentially, inner product absolute value is less than or equal to the product of norms. That's what it says, right? And we also looked at how to prove it. Okay, so today we will continue with the inner product. Let's look at another inner product space. Okay, so let's start with an example. So what is this example? I'm going to take set of all n cross n matrices. Okay, so this is how I'm going to write. It is all those A such that this A belongs to Rn cross n. Okay, it's basically set of all n cross n matrices. Will it form a vector space? Yes, right? You agree? We saw that in the, I think, in one of the classes earlier. The set of all 2 cross 2 matrices formed a vector space. So this forms a vector space, right? So this is a vector space over what? R, right? R is the field Okay. Now I have to, well, I can think of these matrices as vectors. How do I think of these matrices as vectors? I can stack one column below the other and get a very big vector of dimension n squared by 1, and therefore that's a vector, right? So I can still think of it as a vector. But let's restrict ourselves to the set of all matrices. Let's not stack it, but it turns out that it's equivalent to that. So now how do you define the inner product here? So this is a vector space. Now, is it possible to define some sort of a dot product kind of thing here, which is called inner product? So how do you define inner product? You take two matrices A, B. What is the inner product? Yes? I cannot say A, B, right? A times B. Because it gives me a matrix. I should get a number. So how do you get a number from a matrix? Huh? What are the possible things that you can do? Huh? Sorry? Transpose? You are saying A transpose B? Huh? Well, this is still an n cross n matrix, right? It's not a number. So how do you convert this into a number? Huh? Okay, so let's look at determinant. I haven't even spoken about determinant yet, right? So if you have determinant of A, B, right, it gives me a number, fine. But is it linear in A and linear in B? That's also we need, right? Is determinant linear? Well, not really, right? It's highly non-linear, because if you look at determinant of A, that's a polynomial in the entries of matrix A, right? You'll have A power n and A11 power something and so on, right? So it's highly non-linear. So I cannot use determinant. What else I can use? Huh? Trace, right? So that's something that sum the diagonal. Take the product of two matrices, sum the diagonal. That's all. Right? So it's linear in A. It's very clear, right? Trace of A plus B is trace of A plus trace of B. Very simple, right? So sum of the diagonals of the sum is the sum of the diagonals, right? So, okay. Is this clear? This is definitely a inner product. Why is that? For example, if I look at A, what do you get? Trace of, well, I get A squared. What is the issue here? Is trace of A squared always positive? Huh? But I have to ensure that this in A inner product with A is always non-negative, right? But if it is negative, then this is not the right way to define inner product, right? So how do you ensure that? Essentially, what I have to do is I have to ensure that the sum of the diagonals is positive, right? Non-negative. Or if I can ensure that the diagonal entries are also, all the diagonal entries are non-negative, that's also fine, right? How do you ensure the diagonal entries to be non-negative when you look at A inner product with A? There's one way, right? So I'll put a transpose here. So what do I get here? A transpose A. Okay, what do you get in the first 1,1 entry? What do you get? So what is the first entry in the diagonal if I look at A transpose A? So let's look at that. Let's write the picture. So you have this big matrix. This is the first, let's look at the first column of this. This is A, right? This first column, right? Now what is A transpose? That goes here, right? A transpose, if you look at the first row, that's nothing but the first column of A, right? So this and this are both same, right? If that's like you take a vector and take the transpose and multiply with the vector. A transpose A. What is A transpose A? Positive, right? Non-negative. What about the second? Second row here is the second column of A, right? So that corresponds to this. Now when I multiply this with this, I get another positive number. This is 2,2 entry, right? And so on. So all the diagonal entries will be non-negative. Okay. So this will be greater than or equal to 0. When will it be equal to 0? Well, all the diagonal entries should be equal to 0. When will all the diagonal entries be equal to 0? When A transpose or AI transpose AI is 0, right? When will that happen? AI is 0. That means it should be AI should be 0 for every I. That means the entire matrix should be 0, right? Well, it's consistent with our definition. Okay, so now that means I have I have a good inner product. So now I have to basically take that inner product and use it to get the norm, right? So what is the norm, induced norm here? What is the induced norm? This is square root of trace of A transpose A, right? What is this, by the way? If you look at trace of A transpose A, what do I get? I'm taking the first row, first column, multiply with itself, second column, multiply with itself, and so on, and then adding them. If you look at first row, multiply with first row, what do you get? First entry square plus second entry square, and so on. The second row, what happens here? It's the entry, all these entries squared, right? And you are adding them, right? You are taking trace, by the way. So in other words, this trace of A transpose A is nothing but you square every entry of the matrix A and add them, right? That's what it turns out to be. And if I take square root, that gives me a norm, right? What is that norm called? There is a name for it. It's called Frobenius norm. Is that okay? Fine. So this is how you get Frobenius norm. Well, you might ask a very important question. Can we come up with other norms? The answer is yes. You can come up with other norms here. Okay, there are uncountably many norms that you can come up with. Right? We will see how to do that, but soon. But keep that in mind. This is not the only norm. This is an easy norm to deal with and most famous norm. Right? Okay, you have a Frobenius norm for matrices. Okay, fine. Okay, so let's move on now. So let's look at a few other geometry of these vectors. So we have the notion of inner product, we have the notion of norm, right? So what else we need? So eventually I want to solve some set of algebraic equation, right? Like Ax equal to B kind of thing. And we also saw that if A is diagonalizable things, or if A is diagonal, things are good, right? It's easy to find the solution. So now an important question is, when can I simplify this matrix A, right? So in order to do that, let's look at a specific in order to achieve that, the first decomposition that we are going to study, we need something called we studied basis, right? What are bases? Linearly independent vectors that span the entire space, right? But I can have a nice set of bases called orthogonal bases, right? What do you mean by that? Okay, so what do you mean by orthogonal, right? We say that, just give me a second. I hope there are no. Okay. We say that the two vectors V, W belonging to V are orthogonal. So when do you say that the two vectors are orthogonal? If, yeah, so when you take the dot product of two vectors, if it is 0, they are orthogonal, right? Perpendicular. So how do I generalize this? You take inner product of these two vectors, it should be 0, right? Then we say that the two vectors are orthogonal. When do you say that it's orthonormal? We say that, and I'll continue here. Okay, so and orthonormal if, what are the conditions? First of all, it has to be orthogonal, obviously, is 0. And what is the second thing? Normal means what? I mean, it should have unit length, right? So the norm of V should be equal to 1. Okay, So typically this norm is induced by the inner product. Okay, so you should not use completely different norm for normalizing and inner product. Okay, so is this fine? There are several examples, right? So what is an orthonormal basis in R3? Easy, right? 1 0 0 0 1 0 and then 0 0 1 basis. Are there any other example of orthonormal basis in here? What is that? Okay, so you have to think about it, right? So something like maybe I'll give let me make my life easier. So in R2, let's see, I have for example 1 by root 2 1 by root 2. If you look at Euclidean norm, this has norm 1. Okay, now I want to come up with the basis. This is one vector, right? What will be the other vector? Minus 1 by root 2. So these two vectors form an orthonormal basis. Okay, so in other words, if the basis turned out to be orthonormal, then we call that as an orthonormal basis, right? Okay, now the other thing is, if you are dealing with orthonormal basis, it's very easy. Okay, so things are nice because I can take the inner product of the two different bases will be 0 and all that. Okay, so it's very simple and straightforward. Therefore, given a set of vectors, I should always be able to come up with orthonormal vectors. Now, the question is, how do you do that? For example, let's say I have these two vectors, okay? Or maybe these two vectors will form a basis. Do you agree? Huh? So I'll call this as V1 and this is V2. These form a basis, right? Do you agree with this? R2, that means you give me any vector in R2, I can write it as linear. Very intuitive. But are these orthonormal? First of all, it's not normal. It will have different lengths. Secondly, it's not orthogonal, right? They are not perpendicular to each other. But can we come up with a orthonormal basis using this? So what is the procedure? Well, pictorially, I can say, I'll draw a perpendicular here and do it. Well, two-dimensional, yeah, you can manage. Three-dimensional, also you can somehow manage if you have good imagination. But fourth dimensional is hopeless, right? So you don't know how to do that, right? So what do you do? First of all, the first step is I'll normalize this, okay? To make it a unit vector, what do I do? Let's say I do V1 over norm of V1, okay? So in other words, think of it as a Euclidean norm, right? Square of the sum root. So this gives me a unit vector along the direction V1, okay? Is that fine? So I call it as U1. So U1 is a normal vector along the direction of V1. Now I have to come up with another vector which is orthogonal to this. How do you come up with the orthogonal vector? Suppose by some means, let's say, I could get this. What is this? How do you find this? Huh? Projection, right? So what is projection? Well, I haven't taught you what projection is, right? So what is a projection? Huh? So essentially I have to take, so if I want to project V onto U, it's V transpose U, right? In Euclidean space, right? So this is nothing but, the length of this is nothing but V2 transpose U1. I'm going to project onto U1, unit vector, not V1, okay? So I'll project it onto this, okay? Now I have to come up with a vector that is orthogonal. How do you find the orthogonal vector now? Now you look at this vector, no? So this vector is orthogonal, right? So what is this vector? Let me write it here. What is this vector? This vector minus this vector, right? That will give me the orthogonal vector. What is that? What is this vector? I have to move by a distance along the direction of U1. I have to move by this distance, right? What is this distance? This distance is given by the inner product, right? U2 transpose V2 transpose U1, right? but along the direction of u1. So let me write it, or I'll do one thing. So this vector, I'm sorry, it's very clumsy, but this vector is what? I have to go in the direction of u1, so it will be u1. But how much? v2 transpose u1 distance have to go, right? This will be the vector. So what is the orthogonal vector? It's this minus, so v2 transpose u1 times u1 minus v2, right? Right? So now this is the vector that we get, but is it orthogonal to u1? Is it orthogonal to u1? So how do you find that? How do you find that? You have to take the inner product and see, right? So, or dot product in this case and see. So how do you find that? u1 transpose times this will give me the answer, right? So what is u1 transpose u1 minus u1 transpose v2, right? That's what we get. You agree? So how do you, is this correct? Did I make any mistake? Yeah, so this is u1 along the direction of u1. Yeah, this is okay. So now u1 transpose times, I have to see this whether this is orthogonal or not, right? u1 minus v2. So what do we get now? What do we get? So u1 transpose u1 is what? 1, because it's a unit vector, right? So the first term will be v2 transpose u1 minus u1 transpose v2, but u1 transpose v2 is same as v2 transpose u1, so this is 0. So it's orthogonal, right? This is correct. So I get an orthogonal vector. Is that done? I got orthogonal basis now. It's orthogonal, but is it orthonormal? No. What do I do? Divide it by norm, right? So all that I have to do is, if I call this as u2, right? Let me call this as u2 dash. Okay. What should I do? u2 dash divided by norm of u2 dash is u2. I'll call u2 as u2 dash divided by norm of u2 dash. This gives me normalized. So u1 and u2 will give me orthonormal vectors, right? So what is this process called? Any idea? What is this process called? Simple geometry, right? High school, right? So what is this process called? This process is called Gram-Schmidt's orthogonalization procedure, right? Heard of it or no? No? Hey, linear algebra, if you had taken linear algebra, most likely you would have in math you haven't studied linear algebra, you haven't studied Gram-Schmidt's? Yes or no? At least you tell me. Yes. This is what, right? But you should know this, right? So is this strange? Okay. So by the way, you can apply the same thing for your functions also. If I give, let's say, f1 through fn, n functions in the function space, right? I can think of it as a vector space with an inner product and so on. You can use exactly the same procedure to get n orthonormal functions. Okay. This is at least to Fourier and all that. Anyway. Okay. So let's generalize this. What should we, how do we generalize this? Wherever I divided by the norm, I'll divide it by the general norm. Wherever I did the dot product, I'll do the inner product. Okay. So let's look at the process. So this is Gram-Schmidt's. I hope the spelling is correct. Yeah. So what should I do first? Let's say the first thing is given, let's say n vectors. Okay, v1, v2, etc., vn. So in earlier case, we were given only two vectors, v1, v2 in 2 dimensions. This could be in any dimension. In fact, any vector space with an inner product. Okay. So what is the first thing that I do? I get u1, right? u1 is v1 over norm of v1. Done. This gives me a unit vector along v1 direction, right? What do I do after this? I should find a vector orthogonal to u1. So what do I do? Let's look at this, right? I have u1, then I found this. I took inner product, scaled it, and subtracted from v2, and then normalized it, right? So how do I write that? So what is the first thing that I have to do? I have to take v2 inner product with u1 and go along the direction of u1, subtract v2, right? So we subtracted v2 from that. Yeah, so subtract v2, right? So this gives me what? u2 dash. Now what do? u2 is u2 dash divided by norm of u2 dash. You can check that these are orthogonal and orthonormal. Okay, so what is the third step? See, now things will change, right? You have two vectors, and so u1 and u2 are two vectors which are orthonormal. Now I have to come up with the third vector which is orthogonal to both, right? So how do you do that? What do you do? What is it that you will do? Huh? What do you do? If you have third vector like this, and I have to project onto v1 and v2, right? I have to project, huh? So how do you do that? So how do you project onto a plane, right? Or I can write it in terms of geometry. So it's like this, right? You have these two. This is, let's say, orthogonal, and you have a vector like this, which is not orthogonal. It's like this. So how do you project? What do you mean by projection? So let's do this, okay? So I project it onto some point here. So what is this point? This point is a linear combination of u1 and u2, right? Do you agree? Let me call this as alpha 1 u1 plus alpha 2 u2. Okay? This is the point. And when I project, what do you mean by projection? So this should be orthogonal, right? Do you agree? That means this vector should be orthogonal to this vector, right? So how do you ensure that this is orthogonal to this? Right? Let's try to do that. Let's take the projection of, let's say, alpha 1 u1, alpha 2 u2. I'm going to project, right? So if I project onto that, right? So the projection itself will give me this, right? So you agree? So now I want to ensure that this is orthogonal. How do I ensure? What do I do? So basically I have to project, right? That's the idea. Okay, so what I'm going to do now is, we'll come back to this, right? How do you do projection? So let's say, intuitively, you know what projection is, right? You would have done that in your graphics and so on. So I'll use a symbol called proj, okay, which will project, okay? Think of it as a black box. I'll call it, it will project the vector for me. Okay, now what do? I have u1, u2. I take v3. What do? I project v3 onto, I'll project, okay, v3 onto v1 comma v2, okay, some span, some linear combination of this. So it forms a vector space. I'm going to project it onto that, right? This is a subspace, right? v1 v2 is a subspace. So I'll project onto that. Is that fine, everyone? So this projection will give me this vector, right? So if I project, what do I get? Let's say I get this vector. Maybe I'll use a different symbol. Maybe I'll use bar here, okay? So this will give me a vector, okay, which is here, right? What should I do now? What should I do? I should ensure that this is a unit vector. How do you know that this is a unit vector? Right? I don't know. It's not really a unit vector. So what should I do after this? Any idea? So I got this vector, right? I have to subtract v3 from that, right? So what do I get? Orthogonal. And what should I do? I should of V3 minus V3 to get what? U3, right? Now what do? You project V4 onto V1, V2, V3, subtract V4, divide by the norm. I get U4. Keep on doing that. Okay? Is that fine? Is that fine? Okay? Yeah. So now, okay, so now we need to look at what is this, right? So what do you mean by projecting onto a space, right? So what do you mean by that, right? So how do you project, and what do you mean by projecting onto this, and so on, right? So how do you ensure this thing, right? Let's look at this. So for example, okay, this again geometry. Okay, let's look at 2-dimension only. So if you're projecting, this is the point, right? When you project, you get this point, okay, or in other words, you get this distance, right? Length, right? Not really length, but this distance. If it is negative, you'll get negative, right? So that's what we have. Now when you project, so what happens is, suppose if this is your projection, what will you get? You get this vector, right? But if it is here, you get this vector. Among the three vectors, which one will have, which one do you think have the smallest length? There is this vector, there is this vector, there is this vector. Let me call this one as 1, this one as 2, and this one as 3. Okay, so which one do you think has the least length? 1, right? So in other words, looks like if you project, it will have the least length, right? So now we can actually prove that also, right? So how do you prove that? So for example, if I project, so this is, what is this, by the way? This is, if I call this as V and this as U, or the other way, let me call this as U and this as V. What is this? This is some alpha U, right? Do you agree? I'm just scaling it, but I don't know what that alpha is. But alpha U should be close to V, right? That's how I have to scale, right? So what does this problem? This problem leads to what? See, within linear algebra, there is an optimization problem, right? So the distance between alpha U and V should be minimized, right? Of course, the only flexibility that I have is alpha, because given U and V, I mean, U and V are given, right? So what is this? How do you find distance between two vectors? How do you find distance between two vectors? Norm difference, right? So let me look at norm difference, alpha U minus V norm. Minimizing a norm is same as minimizing norm squared also, right? So I can write it like this. Okay, so this is same as minimize over all alpha U minus V whole transpose alpha U minus Vy. This is a Euclidean norm. So it's induced by V transpose V, square root is the Euclidean norm. If the square of that is V transpose V. Is this fine, everyone? Right? Okay, so this is same as minimizing. So it will be, first term will be what? Alpha squared. U transpose U is norm of U squared, right? Minus alpha U transpose V minus V trans, so it's alpha times V transpose U, then finally norm of V squared. This is what you have, right? But the last term is independent of V, so I just have to optimize this with respect to alpha. What kind of a function is this? Let me write that. Alpha squared norm of U squared minus 2 times alpha U transpose Vy. U transpose V is same as V transpose U, right? So that's why it's 2 times. I want to minimize this with respect to alpha. So if you plot this alpha, how does it look like? Yeah, it's a parabola, right? So it's a quadratic, right? It means it's like this. This is called convex functions. We will see what a convex function is. But this is something that I can assume because you would have studied this in other courses. So how do you find the minima? Differentiate and equate it to 0. So you differentiate and equate it to 0. What do you get? 2 alpha norm of u minus 2 u transpose v equal to 0. So this implies alpha is u transpose v divided by norm of u, right? So that means what is this vector? So I want this alpha u, right? Alpha turned out to be that. Alpha u is what? Alpha u is u transpose v u divided by norm of u, right? That's what we got. In fact, by our intuition, we got the same thing, right? Here also. We look at 2-dimension. See, this is this. U1 is V1 over norm of V1. We got this exactly same. Do you agree? Now, this will give us a way, right? So, how do you find U1 and U2? I mean, how do you do this for 2-dimension? What do you think is the solution? Yes. What do you think is the so it's definitely this should be orthogonal, right? For V2. So what should be alpha 1, alpha 2? See, here alpha turned out to be what? Alpha turned out to be a function of V, right? So this is alpha. It's a function of V, the other vector, right? So similarly, what do you think will be this thing? So suppose I have, let's say, V1, V2, and V3. There are 3 vectors. I have converted this into U1, U2, and this is what I'm looking for, right? U1, U2 are orthonormal. I know how to do that. But U3 is the issue, right? So what do you think this should be? So first thing is I'll construct a vector, let's say V, which is alpha U1 plus beta U2. Okay. This corresponds to this point, right? But that point should be orthogonal to what? So this is the point, but if I subtract V2, right? So this is nothing but this point, this vector minus this vector is V3, right? So that should be orthogonal to what? Itself. Do you agree? Is that fine, everyone? Okay, so this should be, now we have this vector. So what we should be, so if you look at V minus V2 should be orthogonal to V, right? That's what we want. You agree with this? Right? V minus V2 is the orthogonal vector. That should be orthogonal to V itself, right? That's what we get, right? So what does this translate to? V minus V2 transpose V is 0, right? So what is V? V is alpha U1 plus beta U2, right? This is V minus V2 transpose, again, alpha U1 plus beta U2 is 0. I want to have this, right? So is that fine, everyone? It's okay. This should be orthogonal to, the difference is orthogonal to this, right? So if I choose alpha and beta such that this happens, then I'm done. I have found the vector V, right? So which is orthogonal. Then everything, you can move forward. Now I will leave this as a homework problem. So you're supposed to find this alpha beta. How do you find this alpha beta? Okay, so there are other ways of figuring this out. So for example, this is the vector, and let's say this is 3-dimensional vector. This is alpha V1 plus beta V2, and this is, or let's say U1 U2, right? That's what we had. U1 U2. This is what? This is some V3. I want to minimize this distance. So that means alternatively, what do we have? I want to minimize the distance between alpha U1 plus beta U2 and V2, right? over alpha beta. It leads to an optimization problem, right? Do you agree? So already we have an optimization problem here. Okay. So now essentially, if you solve this, you will get alpha beta, right? Now if you plug in that alpha beta and get alpha u1 plus beta u2, that's the projection vector of v2 onto the span of v3 onto span of v1 v2, right? That's, or u1 u2 for that matter, right? And you normalize that, you will get, I mean, you get the difference and then normalize the difference, you get v3. Keep on doing that. So what is projection now? Projection attempts to do this, okay? This is projection. Projection of, okay, so I think I should teach you one more thing. Let's say minimize over all alpha beta. So what do I get? I get, let's say, okay, so what I can do is I can call this vector as v, okay? This vector as v. Instead of minimizing over all alpha beta, I can minimize over all v belonging to span of v1 v2, right? That's what I have done. Alpha beta, if I vary, I'll get different vectors in the span of v1 v2, right? It's equivalent. So if I find such a vector, so this argmin will give me the vector v that will minimize, right? So this is nothing but the projection of v2. I think this is v3, right? Sorry, I'll write this is v3. Projection of v3 onto span of v1 v2. Okay, so keep this in mind, because if you look at many of the machine learning problems, what happens is you find the neural network weights and you want the neural network weights, the norm squared should be small, right? So you have to project onto some space. So exactly this is the problem that you will solve. Keep this in mind. Is that fine? How many of you know regularizers in data or neural network? Anyone used have programmed or programmed a neural network or trained a neural network in Python? Model.fit. How many of you have studied model.fit? No? Yes or no? Nobody? Okay, one guy. Okay, good. You? So you have used. So what are the parameters there that you give? Learning rate. We will see what that is later in the class. Yes. Optimizer. Good. We will also see what that is. Loss. For example, squared error. If you look at this squared error is a loss. There is many losses. Fine. Model parameter. Essentially, it says how the neural network architecture is. Okay. Data. Okay, you haven't used regularizer. Okay, so you can add regularizer to as a part of the loss function, or you can also specify as a separate regularizer, right? So essentially it says the norm of the neural network weight should be small, right? We'll add that as lambda times norm of W, right? Why? Because I don't want the neural network to, so I should restrict my choices of neural networks. How do I restrict? I'll make sure that the norm of that is less than or equal to something. So basically it should be within some space, right? So I cannot choose any neural network I want. That's called regularizer, right? So the moment I add that, or if that is a set, I have to project onto that. So projection is exactly this problem. Okay, so we will revisit this later. Okay, now you know Gram-Schmidt's, right? So we can again refer to the notes or the textbook that, or the notes that I have written. So you can go through the chapter on, or whatever the part of the notebook where I have described the Gram-Schmidt's in detail. Okay, for a general vector space V. But I think this is clear, right? Whatever I have done. Is that fine? In fact, I can do the same thing for many other vector spaces also, function space, whatever, right? So same technique will work. So what is the solution of such problem in functional spaces? Same thing, right? It's quite interesting. Do you agree? If I want to project onto something, the solution will be very, very close to what we have. It's just that the language is different. Instead of saying U transpose V, you'll say inner product of something with something. That's all, right? It's quite general. Okay, so we will also solve the same problem using, for example, using, let's say, the optimization techniques. Okay. Okay, any questions? So maybe I'll pause for a minute and then we will move on. Any questions? No? No questions? Those who are online? Okay. Okay, so if there are no questions, let's move on. So let's look at the use of this, right? So let's see what happens if I have, let's say, a simple 2 cross 2 matrix. Okay, so let me call this as A1, this is A2. This is a 2 cross 2 matrix. Okay. What do I do? Suppose I do Gram-Schmidt's. What happens to this? What is the first step? What is the first step? I take A1, normalize it by A1, right? So that's what I'll do, right? What is A2? I will subtract and then normalize, right? So whenever I normalize, I'll get a number, right? That's all it happens, right? So let me write this. Okay, so A1 by norm of A1. The other one would be A2 minus A1 by norm of A1 divided by norm of A2 minus A1 by norm of A1, right? So this is what I get. Do you agree? This is the vector, right? Okay. So now what transformation led to this, or can we go back and forth, right? So now this is a normal vector. If I want to get back the original, what should I do? What should I do if I want to get back the original? Huh? So now, how do you get A1 from this? All that I have to do is scale it with the norm of A1, right? Somehow, right? Then I get A1, right? How do I get A2? A2 is not so straightforward, right? So how do you get A2 from this? First of all, I have to add A1 by something, right? So if you look at this term here, what is this? This is basically some linear combination of A1 and A2, right? Do you agree with this? This is combination of A1 only, right? The second column is a linear combination of A1 and A2, okay? So instead of bothering about what are those coefficients, what I will do is I will write this like this, okay? The first column is alpha A1, okay? Alpha is 1 by norm of A1, right? What is the second column? Let's say if you go back, this is some complicated constant times A1, some other constant times A2, right? So I'll call this as some alpha, okay, beta A1 plus gamma or nu A2, right? This is what you have, right? So this gave me orthonormal vectors. These are our orthonormal vectors, right? You agree? So what is this, by the way? Can I write this as a product of two matrix? What should I do? The first column, this is, how do I get this? So if I have a matrix A1, A2, how do I get this? This is the first column, right, of this. How do I get this? I have to select this column, but with the multiplication of alpha. So this is how I do, right? You agree? So if you multiply, it will only select the first column, right? Do you agree with this? Well, actually, I don't need to do this. So if I multiply by this vector, I get the first column of this. How do I get? So this is given by this. What about this? What should I do? Huh? Huh? What should I do? Again, I'll write it as A1, A2. So what should I multiply so that I get this? So I should select A1, right? But I should multiply it by beta, right? And I should select A2 but multiply by nu, right? So this will. So overall, how do I write this? A1, A2, right? Times what? Alpha, beta, nu, 0, right? Do you agree with this? Yes or no? Huh? Do you agree with this? Right? If I multiply this matrix by the first column, I'll get the first column here. If I multiply with the second column, I'll get the second column here. Right? Do you agree with this? Okay. So essentially, I have written, so this is not my intention, so I have to write it in a slightly different fashion. But nevertheless, okay, so now what kind of matrix is this? What is this matrix called? See, there is a 0 here. What is this matrix called? Upper triangular matrix, right? Now, what is the inverse of an upper triangular matrix? Huh? What is the inverse of this? Let's see. What is the inverse? Can you compute and tell me? Simple 0, alpha, beta, nu. Okay. Simple matrix like this. What is the inverse? I haven't taught you what inverse in this class is, but you would know what the inverse of a matrix is, right? Adjoint of A or determinant of A and all that. Can you try? Hmm? What will happen? See, if you look at this, right, I should remove this, you will get new. So some number. If I do this, I remove this and this, I'll get 0. So 0 will go here. And similarly, I do this, beta will come here and new. So it's an, what do you get? It's an upper triangular matrix, right? Do you agree? Huh? Do you agree with this? Right? So that means this is A, this is upper triangular matrix. Will it get lower triangular? Yeah, you'll get lower triangular matrix, right? Sorry. So now this I will call it as Q. Okay. Okay. So what should I do? Now let me write this. Q is A times U. Right? This is what you get. So what I'm going to do is I'm going to multiply by U inverse on both sides. What do you get? This will be A, right? So A will be Q U inverse. What is U inverse? Lower triangular matrix, right? Right? Or I'll write this as Q times R. Okay. So this is called QR decomposition. So what is so special about this? Let's look at what A is. Okay. What is A? The first column is U1, second column is U2, right? So let's look at that. So A, if you look at Q, for example, the first column is U1, second column is U2. What can you say about U1 transpose U2 or U2 transpose U1? What can you say? How did you get U1, U2? Gram-Schmidt's orthogonalization, right? So what is this? 0, right? What can you say about norm of U1? Which is 1. It's orthonormal, right? So now if I take Q, right? Well, if I take Q, right, or I'll take Q transpose Q, what do you get? Q transpose is what? U1 transpose this way, right? U2 transpose this way times U1, U2, right? This is what we get. So what is U1 transpose U1? 1. What is U1 transpose U2? 0. What is U2 transpose U1? 0. What is U2 transpose U2? 1. You get identity, right? So Q transpose Q is identity matrix. Okay, is that fine? Okay. So now, so in other words, I can take any matrix for that matter and write it as product of QR using Gram-Schmidt's, right? I won't try to prove the general problem wherein A is any n cross n matrix. The procedure is exactly similar, right? You keep on doing the Gram-Schmidt's and I can write that as a product. Okay, so now I have Q transpose Q is identity. So suppose I have, let's say, how do I write this? So let me see if I can convince you or use usefulness of this. So what is A? I can write it as Q or X equal to B, right? Now I can multiply by Q transpose on the left hand side. See, matrix multiplication is easy, inversion is difficult, okay? It's a complex operation. So this implies Q transpose Q or X is Q transpose B. Very easy operation, right? So Q transpose B is just a multiplication of a matrix by a vector B. So let me call this as B tilde, right? Now this is B tilde, right? What can you say about Q transpose Q? Identity, right? What do we have? Rx is equal to B tilde. So how does Rx look like? R looks like. So what is this? U is upper triangular, U inverse is lower triangular, right? That means it's lower triangular like this, right? You have entries here and 0 here, right? Times X, X1, X2, Xn, which is B1 tilde, B2 tilde, and so on, Bn tilde, right? So now, when you multiply, what do you get? The first element multiplied by X, this one, what do you get? This, no, there is R11, okay? So there is a number here, okay? So it's not 0. Everything to the right of it is 0. So R11 times X1 is B1 tilde. So X1 is trivial, right? So B1 tilde divided by R11. What happens to the second one? We saw this, right? So there are two terms here, right? So the first term is what? R21 times X1 plus R22 times X2 is B2 tilde, right? Is that fine? Is that clear? It's fine, right? So keep doing that. So you have, so wait, did I? So I got X1. Now this times X1 plus this times X2 is equal to B2 tilde, but I know X1, so I can compute X2. Easy, right? So, and so on. I won't fill this gap. So it means you need not invert a matrix, right? All that you have to do is do QR decomposition. How do you do QR decomposition? You do Gram-Schmidt's orthogonalization. How do you do Gram-Schmidt's orthogonalization? No inverse, nothing, right? It's like computing the product, sum, squared, square root, and so on, right? So it's a relatively easy way of finding the solution to a set of linear equations, right? This is one way. This is called QR decomposition. Okay, keep that in mind. Is that fine? Any questions? This is the first decomposition that we looked at. You have a class after this? Is Professor whose class is next? Philosophy. Is he there? Not yet? Okay. So anyway, I'll stop here. So take home lesson for today is Gram-Schmidt's and QR decomposition. Okay, so Gram-Schmidt's, you go through the notes. QR decomposition, you just Google. There are so many entries, and you can see the relationship between Gram-Schmitz and QR. Okay, I'll stop here. Thank you.